Hey, how's it going?
Hello, it's going fine. How are you doing?
Yeah, pretty good, thanks. You're doing okay. Um, so you had a lot of meetings on your schedule already, so that's good.
Yeah, yeah. It was very nice to talk to folks. I got a great sense for a lot of the science being done at Carnegie,
Oh, that's good. Yeah,
and it was a
excellent.
nice break from writing applications and wrestling with
Yeah.
Fastlane.
Oh man, yeah, yeah, yeah. I don't know, Fastlane, man. They keep claiming they're gonna update that. Like I know, but I don't know. Yeah, it's not good.
Yeah, it's hard to think of a worse system.
Yeah, well, so my wife used to do a lot of freelance proposal writing, and for like a lot of different government agencies, and there was it was like the Defense Threat Reduction Agency, which is this like very small niche kind of thing. Like their system was way worse than Fastlane.
Oh no.
It was like, your browser is not Netscape Navigator 4.0, and so
Oh
it's not
no.
support. Yeah, so that was terrible. But Fastlane is not great either. So um, let's see. So two questions. One is we usually record these talks. Are you okay with that?
That's fine by me.
And we can either just keep it, internal to Carnegie, or we can make the video, visible to anybody who looks on the website. It's entirely up to you.
Okay, I'm fine either way. If you want to make it public, that's fine with me.
Okay, cool. That sounds good. We'll do that. And do you want to just test screen sharing briefly to make sure that
Yeah,
it
let's do
works?
that really quickly.
Yeah.
I'm also trying the PowerPoint's automated subtitling software.
Oh, yeah.
So this is sort of the first time I've tried it. So if you have feedback, if it gets distracting at any point, I guess just let me know.
That's really interesting. I haven't seen that before. Certainly seems like it's working.
It's working so far.
So,
I think when I practiced, it had difficulty with, I say the word Chandrasekhar a lot, and I think it struggled with some of the names, that kind of thing.
Yeah, I got it that time, but
well, we'll see how it goes.
Yeah, well, that's really cool. So that's just like in PowerPoint now?
Yeah, there's an automatic, in the presenter mode, there's an automatic subtitling feature.
Oh, that's very cool. That's good to know about. Great. But yeah, everything looks good there. So yeah, excellent.
Ooh.
All right. Let's see where we're at. Okay, so leave it another 2-3 minutes just for people to arrive. Just wait one more minute. I think we still got a few people joining. So
Sounds good.
Okay, that seems like a good crowd of people. So I think we can probably get started. So it's a pleasure to have Mia de los Reyes join us today to give our lunch seminar. So Mia is an NSF graduate research fellow down at Caltech, where she has been working with Evan Kirby, trying to understand chemical evolution of nearby low mass galaxies. And she is going to tell us today about using galactic archaeology to look at Type Ia supernova physics.
All right, thanks so much. Thank you so much for having me here today, everyone. Again, my name is Mia de los Reyes. I'm a graduating PhD student from Caltech. I will be trying to use this automated subtitling software from PowerPoint. I think it works pretty well. It might have some trouble with names, but hopefully it's not too distracting. All right, so today we're going to talk about probing Type Ia supernova physics. But before we get started, I just want to take a quick moment to acknowledge the communities that have helped make my work possible. So although I'm usually just down the road at Caltech, I'm actually in Toronto in Canada right now. And so I'd like to acknowledge my status as a settler here on the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. And I'll also be talking throughout this presentation about observations that were made using the Keck telescope on Mauna Kea in Hawaii. And so these observations have really only been made possible because Mauna Kea was dispossessed from Kanaka Maoli. So I just want to take a moment to acknowledge that. And thank you for joining me. All right, so why should you care about anything I say during this talk? Well, Type Ia supernovae are really interesting and they're really useful astrophysical tools used for standardizable candles for measuring the expansion of the universe. And we've had this textbook model of Type Ia supernovae for a while, where we have a white dwarf that accretes matter from a non-degenerate companion star. And then once the white dwarf reaches the Chandrasekhar mass of around 1.4 solar masses, it promptly explodes. And this textbook model that we've had for a while. We've known for a while that it's also not the whole picture, that there's probably some other mechanisms involved. And so a longstanding question has been, what exactly is the primary explosion mechanism or the primary channel of Type Ia supernovae? And there are a lot of different models, and I won't go into all of them, but very broadly speaking, we can make new alternate Type Ia models by using the assumptions in the classical model and sort of tweaking them a little bit. So perhaps instead of a prompt detonation, we have a more delayed deflagration. Perhaps instead of a massive Chandrasekhar mass white dwarf, we have a less massive sub-Chandrasekhar mass white dwarf that explodes. Or maybe instead of one white dwarf that's accreting matter from a non-degenerate companion, we actually have two degenerate white dwarfs that are either merging with each other or accreting onto each other. So I'd like to start by focusing on this middle question about the mass of the white dwarf involved in the Type Ia supernova explosion. One of the ways that we can distinguish between different masses and different theoretical models of Type Ia supernovae is by looking at the nucleosynthetic products that these explosions produce. In particular, I care about manganese. I am a fanganese of manganese because it turns out that manganese is pretty sensitive to the mass of the white dwarf progenitor. So for the rough first order physics background for why this is, as you can see here, this is a plot showing from a nice model by Ivo Seitenzal, showing the density of the white dwarf as a function of the overall enclosed mass in the white dwarf. And you can see above this dashed line, above this density of around 2 × 10⁸ grams per cubic centimeter, that's when manganese gets produced. And this is because manganese is produced from its parent nucleus, cobalt-55. At high density, when you deposit energy, you get lower entropy per the energy that you deposit. And so that means when you go into nucleosynthetic freeze out, you don't have as many light particles. And light particles are the things that destroy cobalt-55. And so if you don't have as many light particles, you get more cobalt-55 in the end, and you ultimately get more manganese produced. So from the observer standpoint, what this looks like is if we actually look at the predicted yields from Type Ia supernovae, we can see this in practice. So here I've listed a number of Type Ia supernova models, theoretical models. And on the x-axis, I'm plotting the expected yields, the predicted yields of manganese from these models. Above the dashed line, these are all of the massive near Chandrasekhar mass models. And you can see that they tend to produce pretty high solar or even supersolar amounts of manganese. So here we're looking at bracket notation where solar is 0. So above this is all solar or supersolar. Below the dashed line, we're looking at the less massive sub-Chandrasekhar mass models. And these tend to be significantly subsolar in the manganese yields that they produce. So we really want to measure manganese from Type Ia supernovae. We could do that directly. It turns out it's actually very difficult to do. So you could do this by actually looking at late time light curves from Type Ia supernovae or getting X-ray spectroscopy of Type Ia supernova remnants. This is hard to do. It's especially difficult to measure elements like manganese. You get quite large error bars and you don't get a ton of data points. I think this has only been done for 4 or so nearby Type Ia supernovae. So instead, what we're going to do is to use spectroscopy, stellar spectroscopy, to measure manganese indirectly in local group dwarf spheroidals. So we're going to focus on dwarf spheroidal galaxies in the local group, partly because the local group is really easy to observe. There are a bunch of dwarf galaxies. They have a diverse range of chemical evolution histories and star formation histories. So that makes them useful for as laboratories to test what supernovae look like in different environments. And there's a bunch of them. And in particular, dwarf spheroidal galaxies are really nice because their star formation is pretty inefficient. So their chemical evolution at this point is mostly dominated by delayed events like Type Ia supernovae. And we're going to measure the manganese in the stars in these galaxies using medium resolution spectroscopy. So compared to classical high resolution spectroscopy, where you're maybe fitting one line at a time, one stellar absorption line, we're going to fit many lines at the same time because we have lower resolution. So I'll show what that looks like in a minute. But the reason we want to use medium resolution spectroscopy is partly because it's a lot easier to get a large sample. When you have lower spectral resolution, you're putting your photons into fewer buckets. And so you need less observing time to get the same number of photons in a single spectral bucket. And so ultimately, we're going to use this and get a very large, I think the largest to date, self-consistent catalog of manganese in these dwarf spheroidals. So let me just show you what the data actually look like. In the top left panel, this is the full observed spectrum from one of our stars. And the green shaded regions you can see here are where the manganese lines live. So this measurement is not easy, in part because most of the manganese lines, the strongest manganese lines, are actually in the blue part of the visible spectrum. And so we actually had to commission a new grading on the Keck DEIMOS instrument. DEIMOS is a multi-object spectrograph on Keck. And we had to commission a bluer grading in order to do this. So these are some of the first measurements ever taken with this new 1200B grading. In the bottom panel, I've zoomed in so you can see a portion of the spectrum in better detail. The black points are the observations. And again, the green regions are now where the manganese lines are. And if you look at any single one of these green regions, if you look at just one of these manganese lines, it doesn't necessarily look like a nice Gaussian or Lorentzian stellar absorption profile. So classical, the usual high resolution spectroscopy methods won't work here. But because we're fitting all of the spectral lines at the same time across this entire large wavelength range, we're actually still able to get pretty precise measurements of manganese. You can actually see that visibly here. So the blue line in the bottom panel is the theoretical spectrum, assuming no manganese. And you can tell it's not a very good fit to the data. The red line is the best fit theoretical spectrum. And so the red region actually gives the best fit spectrum with error bars on manganese. And it's actually pretty precise. So we can do this for a lot of stars in dwarf spheroidal galaxies. Now we have manganese abundances. But the issue now is we need to disentangle how much of that manganese came just from Type Ia supernovae. And to do that, we're going to use galactic archaeology. So if you haven't heard a talk about galactic archaeology before, it turns out that most galactic archaeology is plotting abundance ratios against each other. So that's what I've shown here. On the x-axis, we're plotting the overall metallicity, which is traced by iron. And this is really just a proxy for time. In these dwarf spheroidal galaxies, older stars tend to be more metal poor. That's a generally good rule of thumb. So you can really think of the x-axis as a time axis. On the y-axis, I'm plotting magnesium over iron. So magnesium is an alpha element, which is predominantly produced in core collapse supernovae, whereas iron is produced in both core collapse and Type Ia supernovae. So this ratio of alpha over iron, or magnesium over iron in this case, really traces the ratio of core collapse to Type Ia supernovae. And this is illustrated a little more clearly if you actually look at the observations. So the observations are these black points. And at early times, at low metallicities, the alpha over iron ratio is high. And it's very close to the theoretical yield that we expect from core collapse supernovae. And that makes sense because at these early times, only core collapse supernovae have had the chance to turn on. But at some point, type Ia supernovae do begin turning on, and they produce a lot of iron, but not a lot of magnesium. And so they begin to drag this ratio down towards the theoretical type Ia yield. So we get an observed trend that looks sort of like this flat plateau, and then a knee, and then a decline after that knee. In this case, we fit it with a simple linear fit. And we can convert this observed trend into a useful quantity, which we're going to call F1A, or the fraction of metals that come from type Ia supernovae. And we do this just by observing that this red trend shown here is really just a linear combination of the green and the blue, the expected yields from type Ia in core collapse supernovae. So once we know F1A for one element, in this case magnesium, and magnesium is nice because we know what the green and the blue lines are, we're fairly confident in those values. So we can actually solve for F1A. Once we have it, we can use it and apply it to other elements where we don't necessarily know what the green and the blue lines are. And we can actually solve for the yield that comes just from type Ia supernovae. So we can do that for manganese, which is, again, the element that we're most interested in. And when we do that, we can make observational constraints on the mass of the type Ia progenitor. And so that's shown here. So again, we've listed all of our theoretical models and their predicted manganese yields, and the observational constraint from these manganese measurements in sculptor dwarf spheroidal, which is sort of a nice, easy dwarf spheroidal, I think, to work with. So this observational constraint is shown as the gray shaded region. And you can see that this is pretty subsolar. It's definitely less than 0. And so this suggests that sub-Chandrasekhar mass type Ia supernovae actually dominate in this particular dwarf galaxy. But it is close enough to solar that you do still need at least some fraction, 20% or so, to be either more massive type Ia supernovae or this class of type Ia-X supernovae, which might produce more manganese. But this is just one dwarf galaxy. If we start looking at other dwarf galaxies, we see that this result is not quite the same. So here I'm plotting manganese as a function of overall abundance. And we just talked about sculptor. So sculptor are these dark purple points. The small points are individual stars. The large points are binned averages. And we can see that sculptor has quite low subsolar manganese yields overall. And that makes sense. As we just talked about, sculptor seems to be dominated by these sub-Chandrasekhar mass type Ia supernovae. But if we compare with other dwarf galaxies like Leo 1 and Fornax, those are these brighter colored points up here, we see that Leo 1 and Fornax tend to have higher, close to solar manganese abundances. And this discrepancy, even at the same metallicity, this discrepancy of around 0.2 dex in the manganese abundance is actually really large. It's large enough to suggest that there's a real physical difference in the nucleosynthetic source of manganese. So this suggests that in Leo 1 and Fornax, it is actually near Chandrasekhar mass type Ia supernovae that's producing all of this manganese. So now the question is, what's the difference between Sculptor and these other two galaxies? What distinguishes them? And it turns out that the most obvious thing, at least, is their star formation history. So Sculptor, as shown in the bottom right, has a pretty ancient star formation history. It formed all of its stars pretty quickly in one burst that lasted maybe a couple gigayears, and it's sort of been sitting passively ever since. Whereas Leo 1 and Fornax have both sort of steadily been forming stars over the last 13 billion years. So what this suggests is that maybe at early times in ancient dwarf galaxies, sub-Chandrasekhar mass type Ia supernovae dominate, but then there's a transition at later times in extended star formation history environments, and we get more massive near Chandrasekhar mass type Ia supernovae that dominate. So this is already pretty interesting. It's kind of counterintuitive. You might expect that the more massive white dwarfs get formed first, and so they should be the ones to explode first, and you move to lower and lower masses as a function of time. We're actually finding the opposite, and so that alone can put some pretty interesting constraints on theoretical models. There's still some stuff we'd like to do. So far, we've only really looked at 3 dwarf spheroidals with pretty extreme star formation histories. So Sculptor, shown here, is again really ancient. It was really a very, very quick burst of star formation that finished really quickly. And whereas Leo 1 and Fornax are both sort of extreme extended star formation history environments. So we'd really like to look at a broader variety of dwarf spheroidals with a variety of star formation histories. And so that work is ongoing now, because we really want to understand this transition from low mass to high mass white dwarf explosions over time. We would like to know, if it's a gradual transition, if there's a sharp cutoff, And we'd also like to confirm that there is, in fact, this transition. So that's still ongoing work. Before I move on to the next part of this talk, are there any questions so far? I know that I have trouble paying attention on Zoom for more than 10 minutes at a time. So I just want to pause and take a quick breather and see if anyone has questions.
Hi, can I interrupt, Andrew? I'm sorry.
Oh,
I
yeah,
didn't
yeah,
find
for
that
sure.
phrase.
Yeah, go ahead.
So I saw that. Sorry, this is Henrique opening my video here. I saw that in one of your slides you put a non-LT interrogation point. So in giant stars, the non-LT corrections for manganese could be as high as 0.4 dex. So a lot of these measurements that you made could actually go for supersolar manganese abundances if you add manganese corrections. And I was just wondering how that would actually change, or if you have looked in how that would change your conclusion so far.
Yeah, that's a great question. So let me go back and see if I can. So here, yeah, I've included this arrow that has a conservative estimate of the effective NLTE effects. So first, the NLTE effects that Maria and other folks have found is it sort of works in the opposite direction that we'd expect for manganese. So we've tried measuring manganese and other elements in systems like globular clusters, where we have a better sense of what the overall abundances should be. And they should all be pretty close to clustered, and maybe the only dependence should be on the temperature of the star. And we actually find that the NLT effects go the wrong way. So the larger the temperature, we sort of expect that the higher temperature stars, even red giants, the higher temperature red giants should have larger NLT effects. But when we apply the corrections from Maria Bergman and others, we actually find the opposite result. So I think there's still some work to be done on the theory side, understanding NLT effects. That is a good point, that this particular conclusion about which kind of supernovae dominate in Sculptor could definitely change if these NLT corrections are true and this bar moves up over here. We are looking at solar or supersolar type 1a supernovae instead. But it is also worth pointing out, I think, that that would sort of uniformly apply to all of these points in Sculptor and in Leo 1 and in Fornax. So we would still see this discrepancy. And
yeah,
so that,
the discrepancy, but
yeah,
then again, most of them would be near Chandrasekhar mass sources instead of SUB, right?
That's true.
Even
yeah,
in
that's
Fornax, Sculptor, all of them, I think.
Yes, yeah, that would be true. Although I think then we start running into issues in Sculptor and Fornax, we're already looking at close to solar. We'd be running into issues with producing super solar abundances at the metallicities that we expect. I think that's actually quite hard to do in a lot of the near Chandrasekhar mass models. So you're right that the NLT effects are sort of a major uncertainty in our measurements, but I think there's still a question of I think this transition is real of some kind. There is a change in the dominant type 1a channel, and it's sort of just a question of what is the transition between.
Okay, thank you.
Thanks, that was a great question. All right, any other questions before we move on? All right, so far, Galactic Archaeology has told us a lot about type 1a supernovae, but that's not everything. There's more. So the other, oh, sorry, there's something in the chat. Oh, okay, thanks, Andy. Yeah, so Andy points out that, okay, yeah, I mean, everyone can read Andy's comment. Cool. All right, so going back to the big questions about type 1a supernovae, I'd like to turn our attention from this question about the overall white dwarf mass to this question about the number of white dwarfs involved, the single versus double degenerate channels of type 1a supernovae. So to distinguish between these channels, we can use something called the delay time distribution of type 1a supernovae. The delay time distribution is really an impulse function, a response function. It's the response in the rate of type Ia supernovae after a burst of star formation. So that's shown here in the shaded plot. If you have a delta burst of star formation at time t = 0, then the delay time distribution is the rate of type Ia supernovae that happen after that burst. And you can see here that this rate is actually pretty different depending on whether you're looking at the double degenerate or the single degenerate scenario. In the double degenerate case, where we have two white dwarfs that are merging with each other, the dominant time scale of the explosion is really set by how long it takes for these two white dwarfs to merge and in spiral towards each other. You can actually do a back of the envelope calculation and show that if you just plug in gravity, basically, you can compute the time it takes for these binary systems to in-spiral, and you get a power law of around t⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ partly because the models don't really agree on what the delay time distribution should look like, but there are a couple of common features. And one of those features is sort of a sharp drop off after a few gigayears. And this is because in the single degenerate scenario, when you have a single white dwarf that's accreting matter from a non-degenerate companion, you start by having, because of stellar evolution, you start with the most massive white dwarfs and companion stars first. Then you go to lower and lower mass binary systems. And once you get to a low enough mass, it actually gets really difficult to have a white dwarf and a binary companion that are both massive enough for the white dwarf to ever accrete enough material to explode in a supernova. And so we see this sort of sharp cutoff after around a few gigayears or so. So we really want to measure the delay time distribution because it's sensitive to the intrinsic physics of the Type Ia supernova explosion. Unfortunately, we cannot measure the delay time distribution directly because it's an impulse response. We actually have to measure it indirectly by instead looking at the Type Ia supernova rate. And you can mathematically show that if you convolve the Type Ia delay time distribution with the actual star formation history of a galaxy, you'll get the rate of Type Ia supernovae in that galaxy. So instead, we have to measure the rate. And this has been done in the previous literature, mostly by counting supernovae as a function of time in galaxies. And there are sort of two approaches for doing this. One is by looking at large populations of galaxies with known star formation history. So cluster galaxies or field galaxies, if you assume something about the star formation history, and you count Type Ia supernovae as a function of time. In this case, you need a really large population to get a statistically significant measurement, because most of the time when you count the number of supernovae happening in any single galaxy, the number is going to be either 0 or 1. So you need a very large population in order to do this. The other option is to actually measure, count supernova remnants in galaxies, in individual galaxies like the Magellanic Clouds. And both of these methods are pretty consistent with the t to the -1 power law. So there's been a lot of work on this, particularly by Dan Maus and other collaborators. And both of these methods, I've split them up here, do seem to find a t to the -1 power law. But they both have pros and cons. So the galaxy population measurements, as shown on the left, although they have really detailed time resolution, they make this implicit assumption that every galaxy in the population that you're studying, field galaxies or cluster galaxies, they all have the same Type Ia delay time distribution. By counting supernova remnants in the Magellanic Clouds, you don't have that same issue because you're measuring in individual galaxies, but it's really hard to age date supernova remnants. And so you actually really only end up with one significant time bin. So what we'd really like is the best of both worlds. We want to measure the Type Ia delay time distribution in a time resolved way, but we also want to do it in a single galaxy. And we can actually do that using galactic archaeology. So this calculation really hinges on the observation that we made before, which is that alpha elements like magnesium are really tracing the ratio of Type Ia and core collapse supernovae. So you can convert that into a number ratio of Type Ia and core collapse supernovae. And then in order to get the Type Ia supernovae on their own, then you just need the number of core collapse supernovae. And we can also get that from abundance information by looking at the metallicity distribution function. So the metallicity distribution function is sort of what it sounds like. We measure stellar metallicities and then plot them in a histogram. But physically what it's telling us is that in each metallicity bin, how many stars are being formed. And so you can convert that, if you know something about the IMF, you can convert that to the number of core collapse supernovae that we expect in that metallicity bin. So we end up with both of these quantities as functions of metallicity. And because metallicity is a good proxy for time in dwarf spheroidal systems, we can say that we can actually get the number of type 1a supernovae as a function of time. And that allows us to get the rate of type 1a supernovae. We can do the same thing. So this is sort of the observed rate of type 1a supernovae. It depends only on observations. So we can compare this rate with an expected rate of type 1a supernovae. And we can get that by assuming a delay time distribution and then computing a rate from that. So for the delay time distribution, you have to input some model form. In this case, we'll mostly assume a power law with some minimum delay time. And you can convolve it with a star formation history, which again, we can get from the metallicity distribution function. And we can get an expected rate of type 1a supernovae. There is one big issue here, which is that all of our observed measurements in this calculation are all functions of metallicity. And what we really want is for those to be functions of time. So we need to convert metallicity to time. So to do that, we use something that is very creatively called the age metallicity relation, which you can get if you know the star formation history of a galaxy. The main issue is that the star formation history of really old and metal poor systems is hard to measure. So the most common method that's been done for many of the dwarf galaxies in the local group is to use photometries. So by fitting isochrones to color magnitude diagrams. The main issue, and this works for most dwarf galaxies, the biggest issue is that we're looking at Sculptor. And as we know, Sculptor is very old and very ancient. And also very metal poor. And as you can see in the plot on the left, isochrones begin to bunch together when you start looking at really old and metal poor stellar populations. The difference between a 10 gigayear isochrone and a 13 gigayear isochrone is really, really small, often compared to the measurement uncertainties in photometry. And so to get around this, what we'd like to do is get an age metallicity relation like this, but not from photometry. Again, we're going to rely on chemical abundances to give us this information. So we're going to do this by fitting abundance ratios of a lot of different kinds of elements. So alpha elements, which trace core collapse supernovae, iron peak elements, which trace type 1a supernovae, and S process elements, which trace AGB stars. By looking at all of these different types of elements at the same time, we'll get information about different time scales. So core collapse supernovae sort of trace the early times right after a burst of star formation. Iron peak elements from type 1a supernovae trace the really delayed times. And then the S process elements sort of trace those intermediate time scales. So by fitting the observations of all of these abundance ratios at the same time, the observations in this case come both from our medium resolution measurements with DEIMOS, which are shown in blue, and also some high resolution measurements from the DART team, who use the VLT flame spectrograph. So we're able to fit a model to all of these at the same time, the model shown in black, and we get a star formation history from that. And so this allows us, this is a really nice, I think, complementary method to the photometric measurements of star formation histories, because photometry can tell us fairly accurately what absolute ages are. So we know that Sculptor, all the stars in Sculptor are mostly older than 10 gigayears, but it's really bad at resolving the age spread. Whereas chemical abundance information tells us the age spread, but no information about the absolute age. So by combining the two, we can actually, I think, ideally, we'll be able to get a more precise measurement of the star formation history. And so this paper will be on arXiv hopefully in the next week, so keep an eye out for that. But now we have everything, going back to the delay time distribution stuff, we now have everything to compute both the observed and expected rates of type 1a supernovae, and then compare those two. So that's exactly what we do here. Here, what I'm doing is plotting several different pairs of type 1a supernova rates on the left. The dark shaded regions are the observed rates, so the ones computed just from abundance observations. And the lighter shaded regions are the expected rates, where we've input a model delay time distribution. And here, the three different pairs that I'm looking at are, all I've done is vary the power law index of the delay time distribution. And you can already see pretty visually that, for instance, a shallow power law of around t to the minus 0.5, the two dark and light shaded regions, the observed and expected rates are not consistent with each other. We can also quantify this in a more statistical way by looking at the distribution of the percent errors. So if these two agree, if the dark and the light shaded regions agree with each other, the percent error should be normally distributed about 0. And in the case of the t to the minus 0.5 power law, it's not. And you really need something steeper, like t to the minus 1 or t to the minus 1.5, in order for the observations to match with what we expect. We can also do the same thing with the minimum delay time. So now I'm holding the power law index fixed, and I'm just changing the minimum delay time, the shortest time before a type 1a supernovae turn on. And here we can see that very short minimum delay times of around 50 megayears and really long minimum delay times of 200 megayears. Neither of those are particularly good fits. The percent errors are not distributed about 0. So you need something that's just right of around 100 megayears as the minimum delay time for the delay time distribution to be consistent with observations. So as you can see, these are pretty preliminary results. We've so far mostly been able to test this method for discrete values of different delay time distribution parameters. We would like to eventually do a full fit, but so far, at least I think this result shows that our method works and that it is able to distinguish between different delay time distributions. So ultimately, what this has told us so far is that the type 1a delay time distribution does agree with the t to the minus 1 power law and a minimum delay time around 100 megayears. Physically, the t to the minus 1 power law is pretty close to what's been seen before, and it's also very similar to what we expect for the double-degenerate scenario. The minimum delay time is quite long, actually, in comparison with what other folks have found. So many folks who have done chemical evolution models, for example, have found a much prompter channel of type 1a supernovae, which appear to go off after only 30 megayears or so. So again, this is telling us interesting and useful observational constraints on type 1a supernovae. There are still a bunch of things we'd like to do. So as I mentioned, the delay time distribution work in particular is pretty preliminary. We'd like to ultimately measure the delay time distribution non-parametrically. So ideally without assuming any form of any analytic form of the delay time distribution. And we'd also like to try this in multiple galaxies to see if maybe we can see the same transition that we see from manganese. We'll be able to see that as well in the delay time distribution of different dwarf galaxies. So ultimately, we're hoping that these constraints they're pretty unique. They're very different from, I think, previous constraints on type 1a supernova models. And so I'm pretty excited about those. If you're not excited about type 1a supernovae, that's okay, have no fear. There are other things that I'm interested in and I'm also working on. And if you're interested in chatting with me about any of these things, I would be very happy to chat. So the other part of my thesis is actually looking at galaxies from a sort of a totally different perspective, the population level, trying to understand galaxy evolution and looking at galaxies in cosmic voids, super underdense regions in the local universe. So I have IFU data from KCWI of several of these void dwarf galaxies. And hopefully these are interesting for a couple of reasons. One of them is that they're super isolated. Like by definition, they're very isolated. And so they're good for direct comparisons with simulations, which typically model isolated galaxies or might have difficulty matching specific environments. And they're also quite blue and faint and star forming. So they might actually be analogs to high redshift galaxies. So there are a couple of things that we've worked on so far. One of them that is currently underway is looking at the stellar kinematics of these void dwarf systems and trying to really answer the question, do dwarf galaxies form disks? And there have been some indications that this is not the case. So although classic galaxy formation theory suggests that all galaxies form as disks, in 2017, Coral Wheeler did a really nice study with fire showing that isolated dwarf galaxies actually seem to form as puffy systems. And this is backed up by observations of our local group. So that's shown here. On the y-axis, we have the velocity, the rotational velocity over the velocity dispersion. So higher means more disk-like and lower means puffier, more dispersion supported. And most of the galaxies in the local group, regardless of their distance to either the Milky Way or Andromeda, tend to be pretty puffy looking. But one open question is, I mean, all of these galaxies are still in the local group. They're still pretty close to large L-star type galaxies. And so one question is, if we look at void galaxies instead, which are really, really isolated, will we see the same effect? And so we've started to measure this parameter of rotational velocity over velocity dispersion. And we found that these void dwarf galaxies also appear to be pretty puffy. And so maybe this suggests that low mass galaxies, so galaxies below 10 to the 9-ish solar masses in terms of stellar mass, might not actually form as disk galaxies. The other thing that we're hoping to look at is the metallicities of these void dwarf galaxies. So because they're thought to be maybe high redshift analogs, Lambda CDM predicts that because they're so isolated, they're not as evolved as field dwarf galaxies might be. We might expect that these void dwarf galaxies have lower gas phase metallicities than non-void dwarfs. And this is because if we look at the mass metallicity relation, for instance, the normalization of the mass metallicity relation seems to be a function of redshift. So more distant galaxies earlier in the universe's history have fewer metals because galaxies get enriched over time. And this is actually quite a contentious topic in the literature. Several folks have found evidence for a real significant difference between void and non-void dwarf galaxies, whereas other folks have not found any difference at all. And so one major issue with all of the previous studies is that they've typically used either slit or fiber spectroscopy. So they're subject to aperture effects. As you can see here, if you put a fiber on one of these void dwarf galaxies, you're missing a lot of the spatial extent of the galaxy. And so IFU data is really great because it gives us that full spatial extent, and we're able to measure global metallicities in a way that isn't as affected by aperture effects. So that's also work that is underway. If you're not interested in that, perhaps I can interest you in star formation laws. So one of the things that I have worked on is the global star formation law, which is really just the relationship between how much gas is in a galaxy on the x-axis here, and how quickly stars form, the star formation rate, surface density on the y-axis. And Rob Kennicott had this sort of well-known paper in 1998 where he showed that if you plot a lot of individual galaxies on this plane, you find a really nice power law relation with a power law index of around 1.4. And this recipe, this star formation law, or Kennicott-Schmidt law, is commonly used in all kinds of things, especially in cosmological simulations as sort of a subgrid recipe for making stars. But it's also really old. So 1998 was a while ago at this point. And so I worked with Rob to update and revisit this original star formation law. So here I've shown another view of the original data from this 1998 paper, this time with error bars. And you can see the error bars are quite large. And actually, in this case, both the spiral galaxies and starburst galaxies were needed to actually define the tight star formation law relation. With the new data that we have, 2 decades later, we have much better, much larger samples and much more precise multi-wavelength measurements. We're actually able to define this power law, again, with a power law index of around 1.4, just from the spiral galaxies. And there are error bars on these points. They're just so small that in some cases they're hard to see. We also were able to not only look at the original galaxies that Rob looked at, we were also able to expand to other parts of parameter space. So we looked at dwarf galaxies in our first paper, and we found that dwarf galaxies appear to lie pretty far below where the star formation law that the spirals define. So that maybe tells us that the dwarf galaxies, low density systems in general, might not be well described by the star formation law. There might actually be a low density cutoff here. In our second paper, we looked at star bursting galaxies, sort of the opposite end of parameter space, really high density systems. And there's been a lot of debate for a while about whether or not the starburst and the spiral galaxies together define a single relation or if there's actually a break in the star formation law. And we've, I think for the first time, showed that regardless of various calculation uncertainties, we still see evidence of this break. In both of these cases, the largest uncertainty really comes from measuring the amount of total gas in dwarf galaxies and in starburst galaxies. But we showed that even if you account for this, you still start to see evidence of this break in the star formation law. All right, so those are my two tangents about things that I'm interested in. But for now, I'll leave up my main conclusions from this talk on this slide, and I'm happy to answer questions about this, or if you want to chat at a later time about any of the other projects I've mentioned, please let me know. Thank you so much for having me.
Great, thank you, Mia, for a very nice talk. We have plenty of time for questions. If people want to just raise their hand, I will look for you in Zoom and call on you. Let's see, Gwen.
Mia, very interesting talk. So I was curious about these delay time distributions. How many galaxies do you guys have sufficient data, or do you think it would be possible to get sufficient data such that you could actually make these kinds of measurements? Like, what sort of sample size do you think is feasible in the future? Yeah,
that's a great question. I think for now, with the data that we have now, this is probably possible to do in 3 or 4 dwarf galaxies. The limiting factor is not actually the data necessarily. In some cases, let me see if I can back up. In many cases, the limiting factor actually comes from the other parts of the calculation. So in particular, oops, here we go. In particular, getting the measurements for this part. Let me find the plot again. For this part in particular, and that's because Sculptor is relatively straightforward. It had a single burst of star formation. And so the alpha over iron trend is pretty easy to interpret. In other dwarf galaxies like Fornax, so Fornax is more massive than Sculptor, so we have many more stars, but it's also more complicated. We think that it had multiple bursts of star formation. And so maybe using the alpha over iron abundance might be trickier to disentangle, if that makes sense.
Perfect, thanks so much.
Yeah, the other main issue is when we actually get the age metallicity relation. This depends pretty heavily on what we assume about gas infall, for instance. And again, in complicated galaxies like Fornax, this would be more difficult to do. So optimistically, I think we can do this in 5 to 10 dwarf spheroidals. With the data we have now, probably more like 3.
Very cool. It'll be interesting to see if they turn out similar, if they have sort of very significant differences. Very cool. Thank you.
All right, Johanna, you had a question?
Yeah, hi, nice talk. Can you go back to your summary slide for a second?
Yeah, sure.
Yeah, so this is not my area of expertise, but I am, like in other areas of astronomy, interested in non-parametric fitting. And so I was just curious why you think that, like what you think you might learn from the non-parametric fitting to the delay time distributions. Like, is the idea to learn something about what the non-parametric form is, or just maybe a few words about the motivation for that?
Yeah, so part of the motivation really comes from looking at the 2 different types of delay time distributions, roughly, that we expect from the single and double degenerate channels. So we know for the most part that the double degenerate channel should have a power law delay time distribution. There is very little agreement about what the single degenerate model should look like. And so I think what we'd really like to do is see if we can detect deviations from a t⁻⁻⁴ power law. And because we have no idea what the form of this should look like, measuring the delay time distribution in a non-parametric way would, I think, be the clearest way to do that. If that makes sense.
Yeah, that does make sense. And then, so the idea is to kind of let the data tell you what this relation should be.
Yeah, exactly. And if we do happen to find that the delay time distribution is very different from a t⁻⁻⁴ power law, then that's another observational constraint for theorists and for modelers to try to match.
Okay, thanks.
Yeah.
Okay, Drew, I think you were next.
Hi, that was a great talk. I was just curious whether you've explored any other, tried to understand the origin of this break in the star formation rate law by looking at other parameters like, I don't know, like the star formation rate for dynamical time or something. I don't know what. Just what.
No, that's a great question. So we've done that for dwarf galaxies. Sorry, I have to go all the way back to these slides. We've done that for dwarf galaxies. We actually tried to plot the residuals from the star formation law as the function of a bunch of secondary parameters. And we found that there are a couple of things like total gas mass, for instance, that do seem to correlate with how far away the dwarf galaxies are from the star formation law. And also the stellar mass surface density is another thing that seems to affect dwarf galaxies. So I think we have done some preliminary work in this. One of the biggest issues is that the sample of dwarf galaxies we have is really small. This is mostly because it's really hard to measure the total amount of gas in these dwarf galaxies. But so we've looked at that on the low density end. The break at the high density end is a little more difficult, in part because starburst galaxies are even harder to measure other galaxy properties in a meaningful way. So we have tried to look at things like, for instance, the stellar mass of these starburst galaxies, but that actually is really difficult to do. Most of the information that we get from these galaxies these are LIRGs or ULIRG systems. So they're super bright in the infrared, but the infrared gives us degenerate information about the star formation rates and also the mass of the galaxy. Does that make sense? So it's really hard to get like secondary properties for these. So we're still, I think, trying to understand where this break comes from. And we're hoping to have a third paper on that hopefully soon, but it might depend on, it mostly depends on Rob because he's working on Astro 2020 right now. Yeah, I'd love to talk more about this if you're interested in discussing future avenues for work.
Thank you.
All right, Ivana, you had a question?
Yeah, great talk, Mia. So going back to the Type Ia DTDs, what are the prospects for doing this type of work in ultra-faint dwarf galaxies? So that might solve some of your, I guess, extended star formation history problems that you would run into with Fornax, but then I guess the downside is smaller sample sizes in terms of chemical abundance measurements.
Yeah, so Ev and I are actually working on a proposal right now, ideally to get us enough data that we can do this fitting to get the age metallicity relation, because that's really the limiting factor in looking at most galaxies, is whether or not we can sufficiently model their star formation histories in a convincing way. And so we're very limited by how much we can measure things like barium in particular and carbon in these ultra faint dwarfs, but that's the hope. We're going to try to do it. We'll see how it works. And I think if we can get some kind of model for these ultra faint dwarfs, that alone is interesting because we could measure star formation histories from abundances and then compare them again with photometric methods. But then, yeah, we could also try this. I'm actually not quite sure how. I'm hopeful, but I'm not sure how well it's going to work. The other population actually that I do want to mention that I think this could work on, this kind of approach could work on, are accreted dwarf galaxies. So dwarf galaxies that are now part of the Milky Way halo. And I think some folks have started doing this for things like the Gaia Enceladus sausage. There have been some attempts to do similar measurements with manganese. And I think we could also do the same thing with this delay time distribution calculation for some of those galaxies as well.
Mm-hmm. Yeah, that's very cool. I guess with the accreted dwarf galaxies, though, you might run into problems potentially regarding the metallicity distribution and whether it's representative.
Yeah,
that's
for
a whole
sure.
other thing. Yeah, but that's exciting to hear. Thanks.
Thanks, Ivana. Yeah, definitely membership would be a big issue when looking at accreted dwarfs in the halo.
Do we have any more questions? I'm not seeing any, so in that case, let's thank her again for a really nice talk. And thanks everybody else for joining us today.
Thank you. That was great.
Thank you. Thanks again for having
Thank
me.
you,
I really
Mia.
appreciate it.
Really good
Yeah,
talk.
bye.
Really nice.
Thanks,
And
Mia. Very nice job.
the captioning seemed to work really good as far as I could tell.
That's good. Okay. That's
Yeah,
good to know. All right.
Was not distracting. I mean, I was looking at it, but it wasn't distracting.
Yeah. Okay. That's good. I know I saw it a couple of times. It messed up the names, but yeah. All right. Great to hear. Well, thank you so much, Andrew. I really appreciate it.
No problem. Thanks again for a nice talk.
Mia,
Oh, yes.
I wanted to chat with you, but I ended up just putting my name late, so I guess you
Oh,
didn't
yeah.
see
That's
it.
fine.
If you have like 20 minutes or half an hour,
Yeah. I'm happy to
Right.
chat. I can find your email and send you a Zoom link. Would that work?
there is a Zoom link in the spreadsheet
Oh, okay.
you have
I'll take a
access
look
to.
now.
You'll
Yes.
find my name there.
Okay. Perfect. Great.
Yeah.
I will see you then.
After, you can finish up talking here to everyone.
Okay.
And then we can join there. It's okay.
Yeah. Sounds good.
All right, great. And if anybody else, Andy or Erica, if you wanted anything else you wanted to say to me or before I end the call?
Yeah, no, I don't really have a big thing, but so Eduardo Bravo had these yield predictions, and for the lower mass Subchandrasekhar, he had deficiencies of cobalt, nickel, copper, and zinc, and he told me that was because the alpha-rich freeze-out wasn't operating in those lower mass. And I was wondering what you thought of these other elements as potential probes in addition to manganese, or what, there are other issues, like copper can be made in Marder's process, I suppose, but I was wondering if you were considering other elements, or if you just thought that manganese was the best one to use and that was it, or I just wanted
Yeah, so my work with manganese was actually supplemental work. So Evan Kirby, my advisor, originally looked at all of the other iron peak elements, including chromium and cobalt and nickel, and found a similar discrepancy, particularly with nickel, in between Sculptor and Leo 1 and Fornax. So we think this discrepancy is real, and I think that's why we're pretty convinced of the discrepancy. And nickel is in some ways easier to work with than manganese in that it doesn't suffer from NLT effects to the same degree. So the fact that we see agreement between these two different elements, and we did separate analyses, I think is promising. I think it would be nice to also, so one thing that we're trying to do now is to expand this to even more dwarf galaxies, both in manganese and in the other iron peak elements. And it would be interesting to see if the agreement continues. I think that'd be a nice confirmation of a lot of what of our observational results so far.
Okay, thank you.
All right, I guess I will end the call here then. And so you're gonna talk with Eric on a separate call.
Yeah.
Right? So,
Yep,
We
sounds
can
good.
join the other. Thank
okay,
you.
sounds good. Thanks again.
All right, thanks, Andrew. Bye.